Okay, so we continue from what we were discussing last class. Dn was this desired response vector, xn hat x0, this column is called xn column, then one cycle delayed. If it is n, it is n minus 1, if it is 1, it is 0. So, our notation was this. We go up to z to the power minus n minus 1 x n. So, n minus 1 delay, so it is 0, that means minus n plus 1 and w En was what is E0, E1 dot 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 En. At nth clock, what is the filter output? Filter output will be, if you take this row, xn, xn minus 1 dot dot multiplied by this vector. Okay, W0 xn, W1 xn minus 1 and dot dot, that is the filter output. When subtracted from Dn, that will be En, and so on and so forth for all the other indices. So, Dn minus, we are going to minimize the norm square of En, which is actually E transpose n En, okay, and we found out that this gives rise to W LS least squares as that is, we minimize this with respect to the filter weights, the one that minimizes, that gives rise to this, and this tends to the optimal filter R inverse P as n becomes large, that we have seen yesterday. But there is no explicit use of R matrix, that is input autocorrelation matrix, or P vector, that is the cross correlation vector between x of n vector and Dn. That is why we do not have to make any approximation like we did in the case of LMS, where R and P were replaced by so called bad estimates, and we paid the price that convergence was not absolute, but it was only in the mean. This is this thing, this is called pseudo inverse of matrix Xn, actually called Moore Penrose pseudo inverse, also called least squares inverse of Xn. What it does, this matrix, you are trying to make Xnw as close as possible to Dn, so that if you have the error vector norm square is minimum. Then the solution we get is this. If an exact solution exists, that is, you find you really there is a W for which Xnw equal to Dn, then when you minimize En, the norm square of Pn, then you can minimize up to 0 value, because for that solution error is 0. If there is a solution and this one solution exists, Xnw equal to Dn, then the error is 0, which means the minimum norm square of En achievable is 0. All right, which means En itself can be 0, and if n is 0, in that case Dn, you will get W, which under normal circumstances you get by ordinary inverse. That I am showing that suppose Xn is square matrix, also invertible, there is full rank, there is Xn inverse exists. If Xn is invertible, it is full rank. So, Xn transpose also invertible, we all know from basic matrix theory, right. In that case, this Xn transpose, and if it is invertible, Okay. Then x n transpose x n, if we take inverse x n transpose. Now, A B inverse is B inverse A inverse. So, it will be x n inverse x n transpose inverse x n transpose. So, these two cancels, you get x n inverse. So, in that case, if x n is square and invertible, then obviously d n minus x n w, if you equate that to 0, there is a solution which gives exactly d n, that is x n into w gives exactly d n, because that solution is from this equation. If x n is, I am telling again, if x n is square and full rank, so x n w equal to d n, there is a solution, and that is x n inverse d n, and for that the error is 0, right. That is what this pseudo inverse reduces to. From the formula you can see, if x n is square and invertible, x n is invertible, x n transpose is invertible. So, x n transpose x n inverse is x n inverse, x n transpose inverse, and then x n transpose. These two cancels, so you get identity. So, you get x n inverse. So, in that case, the pseudo inverse is nothing but ordinary inverse. Okay. And solution will be just x n inverse d n, whole error is 0 because x n is full rank. So, there is a unique solution x n w equal to d n, that equation, in which case error will be 0, minimum, so norm square will be 0, there is a minimum norm square achievable, and that is the optimal solution, right. So, this boils down to ordinary inverse when this matrix is square and invertible, but not otherwise. All right, this is a very famous thing. All right. Next thing, suppose x n is a random process, you are measuring variance. Suppose you are measuring not even variance, make it more general. WSS 0 mean. You have to estimate RXX k, estimate. So, that means you should have x n minus k plus x n minus 1 x n minus k, n minus 1 minus k, and dot dot dot, maybe you take up to some L. So, it is n minus L minus k. So, total L plus 1, n minus 1, n minus 2 n minus L. So, total L plus 1 cases, C divided by this is what we have, right. If I take this part, this is actually, you can see x n transpose, because x n vector we all know it. If I define x n like this here, or maybe I go up to index 0, x 0 x minus k, all right. So, you have got x 0 as before, x 1 dot 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 x n, x n minus L, L cycle delayed. So, x n becomes x n minus L, then n minus L minus 1 dot dot dot, and this will be 0 minus L, which is also denoted as Z inverse L x n by your notation, right. And this summation is nothing but x n transpose x n minus L. You just take a transpose of this x 0 x minus L. Okay. Okay, I have taken to be k. So, it is not just a bit, it is not L, it is k, just a change of notation. It should be k. x n becomes n minus k, x n minus 1 becomes n minus 1 minus k, like that. All right. So, if you take this kind of thing x n transpose x n minus L, then you get this, because x 0 x minus k here, x 1 x minus k plus 1 next, dot dot dot, x n minus k, x n minus k, okay, x n minus 1 here, x n minus 1 minus k, like that. Okay. So, this will be a good estimate of the correlation. Okay, this will be a good estimate of the correlation. This product, just you have to take the average by dividing by L plus 1, right. But now suppose, so correlation includes variance also. If you just have k equal to 0, then x transpose n x n will be x n into x n square, x n minus 1 into x n minus 1, that is x n minus 1 square and dot dot up to x 0 square, add all the square terms and then divide. So, that will be a good estimate of the variance. Variance is a special case of correlation, right, or x x 0. Now, suppose from n equal to 0 to some n naught, x n has some statistics, okay, some variance, correlation, etc. But after this n 0, the statistics changes. So, now if you are calculating correlation, okay, you are going like this, index 0, 1, 2, dot dot dot, here is your n naught, then n naught plus 1, n naught plus 2, dot 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 dot. Suppose you are here up to this, and suppose you are taking variance as a special case. So, we will be measuring what? You will take x 0 square, x 1 square, x 2 square up to x n 0 square, and then square x n 0 plus 1 square, x n 0 plus 2 square. But remember, during this part onwards, statistics has changed. It's the variance here is no longer the same as the variance here, but you are mixing up. You are mixing up the squared values from here and squared values from here, adding and then averaging. So, you are part of from this, part from this. But as you move along, you should have new variance, isn't it? Not contribution from old, from past should come down. Similarly, more generally speaking, from correlation, suppose you are finding out correlation with the gap k. So, x 0 x minus k, x 1 x minus k plus 1, dot 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 up to x naught x minus n naught minus k, that is fine. But now, the moment you are crossing to n naught plus 1 and n naught plus 1 minus k and so on and so forth, this part you are taking data from this part, but here the correlation has changed, but you are mixing up two domain. This side when correlation R x k had some value. So, if you had just restricted yourself up to this, up to n naught and take the average x 0 into x minus k, x 1 into x minus k plus 1 dot 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 up to x n naught into x n naught minus k, at the average, you would have got very good estimate. But you are now going further ahead, you are bringing now data from the right of n naught. So, from that time after n naught, correlation has changed. So, what you should then do? You should forget this past and start from n naught plus 1, then n naught plus 2, you go further ahead, take lot of samples, just restrict your calculation of variance and correlation only there. Okay. Then there will be no mixing. Okay. Otherwise, in that intermediate stage, when part of this side and part of this side both are present, both are taken into account, then we will have wrong result of variance, correlation, etc. To get rid of this, we will introduce something called a forgetting factor. The forgetting factor will be a scalar which will try to reduce the effects of past okay, into the present computation, past data into the present computation. Let me explain by writing the expression. Suppose earlier you were minimizing this. Okay. There is a 1 by n plus 1 that I am not considering, because that will not depend on the filter weights. These errors depend on filter weight, that we have explained earlier. Earlier you are minimizing this sum of square error. Okay. But what happened? So, what you have here e square 0, e square 1, maybe e square some intermediate point n naught, e square n naught plus 1 dot 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 e square n. Now, suppose up to n naught input statistics did not change. So, if you are restricted your calculation only up to this e square 0, e square 1 up to e square n naught, add them, divide by the number of terms, you will get a good estimate of the previous variance. Or if you start from e square n naught plus 1, e square n naught plus 2 and go up to some e square n, and suppose there are many terms here, just add them and divide by the number of terms, you will get again a good estimate of the new variance. But you are not doing that, you are actually going one at a time. So, after n naught you included e square n naught plus 1. Okay. And this whole sum then we will have one contribution from the current statistics and all other contribution from the previous statistics, and you are averaging. So, that will be neither the variance of previous case nor the variance of the current case, and this will continue for some time till you have got very long contribution from the current n naught plus 1 onwards. You go to n which is very large. So, contribution from this side, right hand side of n naught is much larger than the contribution here, because here the length is up to n naught plus 1, 0, 1 up to n naught. So, n naught plus 1, here n naught plus 1 to n. Okay. So, if this size becomes very long because n is very large, okay, then overall sum will be dominated by this side, which is fine. The past is almost forgotten. But till that happens, there is an intermediate range, transition range, when there will be error, when part of some contribution from past and some contribution from present, they will get mixed up. To avoid that, we introduce a forgetting factor real positive lambda this between 1 to 0. In practice, lambda is close to 1, like 0.99, 0.98, and what we do is this, we modify this summation lambda to the power n minus I, this summation we considered. What is the summation? Let us write down. I equal to 0 means lambda to the power n is square 0, then lambda to the power n minus 1 is square 1 plus dot 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 lambda to the power, this is n naught, forget n naught, I am going to the last point. It was 0 n, it was 1 n minus 1. If it is previous term is e square n minus 1. So, it will be lambda times e square n minus 1 and then just e square n. Okay, when it is n minus 1, it is lambda to the power 1, lambda to the power n minus I. So, if I is n minus 1, n minus within bracket n minus 1 is lambda, lambda to. So, lambda e square n minus 1, and lastly when I equal to n, lambda to the power 0 is 1. So, e square n, this is a summation. Now, in this summation, because lambda is less than 1, even if it is 0.99, as we go to this side to the left, before lambda I have got lambda square, then lambda cube, lambda square, lambda to the power 4. So, as you go into the past, power of lambda is increasing, and lambda is less than 1 means progressively it is becoming less and less, because lambda is less than 1. So, contribution for past is becoming less and less, it is getting diminished, because they are increasingly multiplied by higher and higher power of lambda. So, their contribution is diminished, whereas current term has full contribution, previous term has little less because of lambda, then previous term will be lambda squared, so slightly less. So, our overall contribution of the errors in this summation will be coming mostly from the current En and some of the past Ens, En minus 1, En minus 2, maybe En minus 3, like that. I mean terms which are very remote, okay, like E0, E1, E2, their contribution will be very less because their corresponding power of lambda will be large and lambda is less than 1. So, suppose lambda to the power 10, that is much less, almost 0. That is why so this arrangement will help us forget the contribution from the past, remote past, and concentrate on and allow us to concentrate on the recent. Okay. This means earlier we are considering earlier x transpose y, where x and y, just two vectors I am taking, something big, x transpose y, we are considering, that was called the dot product or inner product between x and y, x 0, y 0, x 1, y 1, dot dot x n, y n, summation. But now we will have lambda x n, y n. Okay. This was x 0, y 0, now it will be x n, y n, current term as it is, then just 1 lambda dot dot dot, this is lambda to the power n, x 0, y 0. So, this is nothing but this when x and y both are same and both are equal to E n vector. So, E n transpose E n, that was the thing earlier, but now that was that summation, but now with lambda summation has changed. So, this will be actually not x transpose y, because x transpose y is this. Now, a lambda has come. So, this is equivalent to, you can see, x transpose, then one diagonal matrix. I will tell you what the diagonal matrix is, y, where is lambda, capital lambda, lambda to the power 1 and lambda to the power 0 is 1, this side 0, this side 0. This lambda n y means lambda to the power n y 1, lambda to the power n y 0, lambda to the power n minus 1 y 1, dot dot dot. Okay. Then x transpose. So, you will have x 0 lambda to the power n y 0, that is what you have here, plus x 1 lambda to the power n minus 1 y 1. Okay, so x 1 lambda to the power n minus 1 y 1 and so on and so forth. This is the expression. In the case of variance, both x and y are E n vector. So, it will be, so now norm square will be no longer E n transpose E n like x transpose x or x transpose y, no longer E n transpose E n, but it will be E n transpose, then this lambda n factor all right. This is what we have to minimize. That means, if we find out as before E n as d n minus x n w, we have to minimize this norm square, which is okay, which means d n minus okay. Now, if you break it, d n transpose which is the new norm square on, in the presence of lambdas, then x n W transpose this. So, that means W transpose x n transpose minus other cross term d n transpose a row vector this plus, but before that these two, as I said earlier, these two terms both are scalars. These two terms are same because one is both are scalar and one is the transpose of the other. If you take transpose of this, W transpose comes first and transpose of this means x n transpose, then this transpose, but this is a diagonal matrix, transpose is itself, then d n transpose which is d n. So, both are same. Okay. Instead of writing 2, I can write 1 and then have twice that I will do, plus the last term x n W transpose means W transpose x n, then this x n W. Which is now I am twice W transpose, this is a vector, column vector, x n transpose lambda n, matrix into matrix a matrix, matrix into column vector d n is a column vector. Overall column vector you can call it U. So, W transpose U, if you differentiate it with respect to all the components of W and put it in a stack, you will get U, that means this only. So, I am first writing and then I will differentiate. Remember, this matrix also Hermitian because this is a diagonal matrix, x n transpose, right, it means the transpose here, x n W transpose. So, W transpose x n transpose. This is Hermitian because if you take its transpose, you get x n transpose here, then transpose of this means transpose of this diagonal matrix which is itself, and transpose of this transposed x n which is x n. So, same as this. This is Hermitian matrix. So, if I have a Hermitian matrix R, W transpose R W, which is a scalar, when differentiated with respect to W, all the components of W and put it in a stack, it will be twice R W, we have seen that. So, now that means after differentiation, if I apply del W on this, I will get twice R and here minus twice this thing. You equate this to 0 and if this is invertible, assume this to be invertible as before. So, your WLS will be inverse, 2 cancels. So, only this lambda n matrix has come. If you take that out, it is same as what we had earlier. Okay. And I am assuming this matrix to be invertible because of this region, that even if this lambda n has come, Okay, this matrix this will be positive semi definite always. We will assume it to be positive definite. Firstly, it is Hermitian, we have already seen. Okay, you can take transpose, we have already seen. It is positive semi definite because if you take a C vector non-zero, okay, C vector non-zero, n cross 1. So, this C transpose, this matrix C. What happens to this? Now, this lambda n, which is lambda to the power n, lambda to the power n minus 1, lambda 1 and 0, you can take positive square root of lambda. So, if I construct these two matrices, I am just denoting by this, and this is square root lambda to the power n, square root lambda to the power n minus 1, square root lambda 1, 0, 0, and again same matrix. You can easily see, if you multiply these two, you get this. All right. So, here C transpose, X n transpose, this square root, and there again diagonal means they are Hermitian, symmetric. And so, I take this part, call it D. So, if it is D, you can easily see this is D transpose, C transpose, X n transpose, and transpose of this is itself. So, this is norm D square. So, always greater than or equal to 0, that is why positive semi definite. But when will be 0? I have to rule out that case. If it is 0, that means D must be 0, norm square, ordinary norm square, d0 square plus d1 square plus d2 square dot dot. If it is equal to 0, everybody is non-negative and adding, so every component has to be 0, then every contribution 0, overall 0. Okay. If d is 0, then that means zero. You call it C1. So, that means this matrix times C1 0, but these are all positive elements. So, this matrix times C1 means what? This square root lambda to the power n into top first guy of C1, then square root lambda to the power n minus 1 second guy of C1 dot dot dot, and if that is equal to 0, and since lambda is positive, square root lambda is positive, then every element of C1 has to be 0. Okay, that is C1 must be a 0 vector. Understood? If you take this matrix lambda n to the power half and take a C1 vector, what do you get? This square root lambda into the power n times first guy, square root lambda to the power n minus 1 second guy dot dot dot, and you are equating that to 0. Therefore, elements of C1 should be 0 because these are not zeros. Lambda is non-zero, square root lambda is non-zero. Okay, so C1 0 vector, and C1 0 means x n C 0, which means columns of x n, since C is a non-zero vector, you can linearly combine the columns of x n by the elements of C and equate to 0. So, one column you can write as a linear combination of the other columns. Columns are linearly dependent. There is a linear relation involving the columns, which we assume not to be not the case, because data is coming purely randomly. There is no linear relation in the background involving them or connecting them. So, this will not happen. So, this is not allowed, okay, because data in x n they are coming randomly, there is no linear relation in those data vectors, that does not happen in practice. Therefore, x n C you cannot find a non-zero vector C, so that if you combine the columns of x n by the elements of C, you get a 0 vector, meaning at least one vector you can keep on the left hand side, which has a non-zero coefficient from here, others you take to the right hand side, divide both sides by that non-zero coefficient. So, one column you can write as a linear combination of the other columns, as though there is a linear relation between columns. One column, there is a formula by which you can get one column as a linear combination of other columns, but that does not happen in practice. In practice, all the data come randomly, there is no linear relation binding them. So, this will not happen. So, for non-zero C, you cannot find a non-zero C so that x n C is 0, because columns of x n are linearly independent. Okay. Of course, this for the same reason I have said earlier, n plus 1 should be greater than or equal to capital N, number of rows should be greater than or equal to capital N, number of columns, that I have already explained, the same logic holds here. Alright. So, this is the more general formula of WLS with a forgetting factor. We will start from here in the next class. Thank you very much.